We're going to take a look at the series, the summation from 2 to infinity of natural log of n divided by n squared. And we want to know if this series converges or diverges. And first, let's try using the test for divergence. So we'll take the limit as n goes to infinity of natural log of n divided by n squared. That's the same as the limit x goes to infinity natural log of x divided by x squared. As x goes to infinity, ln of x goes to infinity, and so does x squared. So we get this indeterminate form, infinity over infinity. We can apply L'Hopital's rule, and this is equivalent to the limit as x goes to infinity, 1 over x divided by 2x, which is the limit x goes to infinity, 1 divided by 2x squared, and that is 0. So the test for divergence is inconclusive. That means we have to try something else. So let's try the integral test. Now the integral test requires a function that gives us the nth term of our series when n is plugged in for x and n is a positive integer greater or equal to 2. There's only one such function. It has to be f of x equals natural log of x divided by x squared, and this is for x in the interval 2 to infinity. The reason starting at 2 is because the series starts at 2. Now we have to verify 4 conditions this function must satisfy before we can use the integral test. First is that f is continuous on the interval 2 to infinity. When we look at this function, it is defined for all positive values of x, and for any x greater than or equal to 2, this function is clearly continuous because the denominator is not 0 and the two parts ln of x and x squared are both continuous. Second condition we must verify is that f of x is greater than 0 for any x in this interval 2 to infinity. When we look at this function, the numerator is positive for anything greater than or equal to 2. The denominator is positive, and the quotient of two positive numbers is always positive. So the second condition is true. The third condition, f is decreasing on the interval 2 to infinity. We just need it to be decreasing starting at a certain point. It could actually, we can show it starts to decrease from 3 to infinity or 5 to infinity. That would be sufficient. But in this case, it will be decreasing on the interval 2 to infinity. So because the numerator is not constant, we're going to take the derivative of this function. This is using the quotient rule, x to the fourth, and in the numerator x squared times 1 over x minus 2x times natural log of x. This is x minus 2x natural log of x divided by x to the fourth, and dividing by x, this is 1 minus 2 natural log of x divided by x cubed. Now starting at 2, natural log of 2 is bigger than 1/2, and 2 times a number bigger than 1/2 is bigger than 1. So this is less than 0 for any x in the interval 2 to infinity. So this function is decreasing. The derivative is negative for anything 2 or greater. We can conclude that this function is decreasing on this interval. And condition number 4 is already been shown the way we selected our function. F of n is natural log of n divided by n squared, and this is true for n equals to 2 or 3 or 4 or 5 or 6 and so on. So function satisfies 4 conditions needed to use the integral test, and the integral test says that the series, the summation from 2 to infinity natural log of n divided by n squared, and this improper integral from 2 to infinity of ln of x divided by x squared either both converge or they both diverge. So we're going to evaluate this integral first by finding an antiderivative of natural log of x divided by x squared. And the way to do that, we'll use integration by parts. We're going to let u be the natural log of x. That means that dv is equal to 1 over x squared dx. du is 1 over x dx. And v minus 1 divided by x. So this integral, the integral of natural log of x divided by x squared, is equal to u times v, which is minus ln of x divided by x, minus the integral of v du, but because v has a minus and this will be plus, v times du would be 1 over x squared dx. So the second integral on the right, the integral on the left is tough, but the integral on the right is easy. This is minus ln of x over x minus 1 over x, which we can write as minus natural log of x minus 1 divided by x. So now we can return to the improper integral. The integral from 2 to infinity of natural log of x divided by x squared is equal to minus ln of x minus 1 divided by x evaluated from 2 to infinity. So this is equal to the limit x approaches infinity of minus natural log of x minus 1 divided by x, and then plugging in 2 and subtracting because we have a minus. This will be plus ln of 2 plus 1 divided by 2. So all we have to do is evaluate this limit. And this limit, first, when we plug in, when x goes to infinity, the numerator goes to minus infinity, denominator goes to infinity. So we can apply the L'Hopital's rule, and this becomes the limit as x goes to infinity minus 1 divided by x divided by 1. And clearly this limit is going to 0. Therefore our integral from 2 to infinity of natural log of x divided by x squared converges to natural log of 2 plus 1 divided by 2. We just want to know if the integral converges or diverges. So now here's our conclusion. Since the integral from 2 to infinity of ln of x divided by x squared converges, so does our series, the summation from 2 to infinity, natural log of n divided by n squared by the integral test. And so we have established that this series converges. Now it's very important to understand what we can conclude from the integral test and what we cannot. Now since the integral from 2 to infinity of ln of x divided by x squared dx equals to ln of 2 plus 1 over 2, it is tempting to think that the series also converges to ln of 2 plus 1 over 2. But that is false. That is not true. We cannot conclude that the series converges to ln of 2 plus 1 over 2. All we can say is it converges to something, and determining what it converges to requires another type of approach. So it's very important that you understand that just because the integral converges to a given limit, the series does not converge to that very same limit. For more videos, visit www.mathprepvideos.com.